Today, we are counting down the top 10 network protocols that keep the internet running, from outdated vulnerabilities to the digital foundations we rely on every day. Across this list, you will uncover hidden risks, layered innovations, and the reason every click, message, and login works or fails. Which protocol claims the most critical spot? Let us kick things off. Number 10, FTP. File Transfer Protocol was once the standard way to move files between computers across the internet. It works by opening two separate channels, a control channel on port 21 for commands, and a data channel, usually port 20 in active mode, for the actual file transfers. In active mode, after connecting to the server, the client must accept an incoming connection from the server for data. This setup often fails today because most firewalls and home routers block these unexpected inbound connections. Passive mode flips the script. The client asks the server to open a random high-numbered port, then connects out to the server for both control and data. While this is more firewall-friendly, it means the server must keep a range of ports open, which can be a headache to secure. Everything sent over FTP, including usernames and passwords, travels in clear text, unprotected from anyone watching the network. That is why security experts recommend using SMTP or FTPS, which encrypt your data and credentials. FTP is defined in RFC 959 and still appears in legacy systems, but its lack of security and firewall challenges make it a protocol best left in the past. SMTP, Simple Mail Transfer Protocol, is the backbone for sending email across the internet, acting like the postal service for digital messages. When you send an email, your client connects to the mail server using port 587. This is the submission port, where authentication is required to prove you are allowed to send mail. In contrast, port 25 is used for server-to-server relay, passing messages from one mail hub to another along the delivery chain. Messages may hop through several servers before reaching their destination, each stop recorded in the email headers. Without proper controls, port 25 once allowed anyone to relay mail, fueling global spam and earning the name Open Relay. Modern servers require authentication for submission and use Start TTLS to upgrade plain connections to encrypted connections, protecting credentials and content in transit. These changes, defined in RFC 5321, help keep email flowing while fighting abuse and eavesdropping, but much of the system still relies on protocols designed before today's security threats. DHCP, Dynamic Host Configuration Protocol, takes the hassle out of network setup by handing out IP addresses and settings automatically. When a new device connects, it broadcasts a discover message across the network asking for a configuration. One or more DHCP servers respond with an offer, each proposing an IP address and other details. The device picks one and sends a request, confirming its choice. The server then sends an acknowledge, finalizing the assignment. This whole DORA process, discover, offer, request, acknowledge, runs over UDP ports 67 and 68 as defined in RFC 2131 and RFC 2132. The assigned IP address comes with a lease, usually lasting hours or days, which the device must renew before it expires. Run ipconfig, renew on Windows, or run dhclient-v on Linux to see this negotiation live. But there is a risk. If a rogue DHCP server appears, it can hand out fake settings, misdirecting traffic, or causing outages. That is why network admins use features like DHCP snooping to block unauthorized offers and keep the network trustworthy. ARP, the Address Resolution Protocol, bridges the gap between IP addresses and physical hardware on local networks. When a device needs to send data to another machine on the same IP version 4 subnet, it uses ARP to discover the target's MAC address. The process starts with a broadcast. One device asks who has this IP address. Every device on the LAN hears the request, but only the one with the matching IP replies directly with its MAC address. This mapping is then stored in an ARP cache for a short period, often just a few minutes, to avoid repeating the broadcast. Running the command ARP-A on most systems shows these active entries. ARP is defined in RFC 826 and operates only with IP version 4. IP version 6 relies on a different system, Sometimes devices announce their own presence with a gratuitous ARP, updating caches across the network. But ARP's trust-based design leaves it open to abuse. Attackers can poison the cache with false mappings, redirecting traffic or intercepting sensitive data. For local delivery, ARP quietly keeps everything running, but its weaknesses make security monitoring essential on every LAN. DNS is the system that turns human-friendly names like example.com into the numerical IP addresses that computers actually use. When you type a website address, your device asks a DNS resolver to find the corresponding IP. If the resolver does not already know the answer, it performs a recursive search, first checking the root servers, then the top-level domain, and finally the authoritative server for the domain. Most DNS queries use UDP on port 53 for speed, but if the response is too large, over 512 bytes, or if a full zone transfer is needed, DNS switches to TCP on the same port. You can see this process firsthand by running a command like digexample.com, which shows each step of the query. DNS responses are cached according to their time to live, abbreviated TTL, so repeated lookups are faster. To protect against forged responses and hijacking, DNSSEC adds digital signatures, while some services encrypt queries using DNS over HTTPS or TLS. Every protocol that relies on names, like SSH or HTTP, depends on DNS to connect names to addresses, making it a foundational part of every online interaction. Number 5. SSH stands for Secure Shell, and it is the protocol that lets administrators log into remote systems with confidence their commands and credentials are safe. Unlike older tools like Telnet, SSH encrypts everything from the moment you connect. No one can eavesdrop or steal your password in transit. SSH operates on port 22, as specified in RFC 4251, and has become the standard for secure server management worldwide. The most common way to connect is with the SSH command. Type SSH user at hostname. For even stronger security, key-based authentication is preferred over passwords. By generating a key pair with SSH keygen, users can store their private key locally and upload only the public key to the server, making brute force attacks far less effective. Disabling root login and requiring keys are best practices for any serious deployment. SSH also powers SFTP and SCP, which reuse the encrypted channel for file transfers. With strong encryption and flexible authentication, SSH remains the backbone of secure remote access. UDP, the User Datagram Protocol, is built for speed. Unlike its cousin TCP, UDP does not set up a handshake or track connections. It simply sends packets, called datagrams, from one device to another as quickly as possible. Each datagram travels on its own, with no guarantee it will arrive in order, or even arrive at all. The entire UDP header is just 8 bytes, minimal overhead, no sequence numbers, no retransmissions. This makes UDP the protocol of choice for real-time traffic like online gaming, live video, and voice calls, where dropping a packet is better than waiting for a resend. Defined in RFC 768, UDP's best effort delivery is a double-edged sword. It is fast, but it is also vulnerable. Attackers can spoof source addresses or launch amplification attacks, especially with open services like DNS. For network troubleshooting, running TCP dump -NUDP shows these lightweight packets moving across the network. UDP's focus on speed over certainty is what gives it a vital role in the modern internet, even if it leaves reliability to the application. Number 3, TCP, Transmission Control Protocol, is the backbone of reliable communication on the internet. Unlike protocols that simply fling data and hope for the best, TCP establishes a connection between devices using a 3-way handshake, SYN, ACK, and ACK, before any real data moves. This handshake sets up the rules, agrees on starting sequence numbers, and makes sure both sides are ready, minimizing the risk of lost or duplicated packets. Defined in RFC 793, TCP is connection-oriented, and it tracks every byte sent and received. If a packet goes missing, TCP retransmits it, guaranteeing ordered and complete delivery. Tools like curl-v let you watch this process in action, showing each handshake and acknowledgement as a web page loads. TCP also manages flow control and congestion control, slowing down when the network is busy to prevent overload. But this reliability comes with a cost. TCP is more complex and can be targeted by attacks like SYN floods, where fake handshakes exhaust a server's resources. Modern systems use safeguards like SYN cookies to defend against these threats. For web browsing, email, and file transfers, TCP's careful courier service is what keeps data intact from end to end. HTTP is the language of the web, setting the rules for how browsers and servers exchange information. When you click a link or load a page, your browser sends an HTTP request, often using methods like GET to fetch data or POST to submit forms. The server replies with a status code. 200 means success, 404 means not found, and 500 signals a problem on the server side. Each request stands alone, with no built-in memory of what came before, making HTTP stateless by design. The protocol runs over TCP, usually on port 80, but most sites now use HTTPS on port 443 to encrypt traffic and protect privacy. You can peek at a site's response headers by running curl-ihttps://example.com, which shows the status code and key metadata. HTTP2 and HTTP3 have brought faster, more efficient connections, but the basics remain the same. Every web interaction starts with a simple request and response. For any sensitive data, HTTPS is essential. It wraps HTTP in TLS encryption, keeping your browsing private and secure. IP, the Internet Protocol, is the backbone that makes every networked conversation possible. It assigns every device a unique address, like 192.168.1.10 for IP version 4, or a much longer address for IP version 6. So data knows where to go. When you send a message across the internet, IP breaks it into packets and labels each packet with source and destination addresses. Routers along the way use the longest prefix match to decide where to send each packet next, forwarding it hop by hop. Each packet carries a value called time to live, abbreviated TTL, which drops by 1 at every stop to prevent endless loops. When TTL hits 0, the packet is discarded. Run traceroute-example.com and you will see each router along the path, each hop reducing TTL by 1. With only 32 bits, IP version 4 addresses began running out, so IP version 6 expanded the pool to 128 bits, solving address exhaustion and making NAT less necessary. Every protocol, whether web, mail, or streaming, relies on IP to deliver packets, making it the foundation beneath the entire stack. I hope you enjoyed the video. There will be a lot of interesting videos coming soon. Subscribe and hit the bell to not miss out on this. See you in the next one.